Thanks for everybody coming here in person, and thanks for those that have joined online. Hopefully, I think all the audio and visual is working. Um, yeah, today we're hosting a student team from the University of Calgary who recently participated in the Imperial Barrel competition and got an honorable mention, and their project was geothermally focused. So they'll be the bulk of the content today, but just to start it off. Let's see. Oh. Just at GLJ, we of course do our land acknowledgement of where we're sitting and that we're on the treaty lands. That include the Siksika, the Piikani, and the Kainai, and the Tsuut'ina and Irihani Nakota. And besides just doing a land recognition, GLJ is a very intent and focused on being committed and involved in Indigenous reconciliation and do that through awareness, relationships, knowledge, and opportunities. And this is just kind of a smattering of efforts that we have been involved in, attending conferences that are Indigenous led or Indigenous focused, making awareness of days of awareness for National Indigenous Peoples Day. And we're also a sponsor of the Prairie Chicken Dance competition that is actually happening today out at the Blackfoot Crossing Historical Park, which is just east of Calgary. It goes till 9 o'clock today. So definitely a good opportunity to go check it out. Um, and we also like to build relationships with the Indigenous people that um, are active in this land. So this is Delaney Bear Chief from the Siksika Nation, and we are very intent on building positive and impactful relationships with our Indigenous partners. As I mentioned, the Blackfoot Crossing Historical Park, which is east of Calgary, you can see the little map there. It's the little blue dot. Calgary's on the left. It's about an hour's drive. It's a great museum. Just a little plug to go out, check it out, learn some stuff. It's a great spot, beautiful location, and there's great content to learn more about where the Treaty 7 was signed. As I mentioned, the Prairie Chicken Dance competition is happening today. We support Indigenous partners through various efforts, both with our technical staff and with our soft skills of getting to know them and supporting uh, reconciliation. And we do lots of reserves and resource evaluation work for them, which can be related to litigation and rightful ownership of the mineral and oil and gas rights. And we do technical studies and support them on CCS type studies. And so for those of you that are not familiar with who GLJ is as a technical company, we're independent evaluators, auditors, advisory. We have a group of engineers and geoscientists that are very focused on all energy types that we can support. We're headquartered in Calgary. We have an international client base, across the globe. Uh, Lots of active projects going on all the time and supporting various types of energy. Our bulk of our businesses has been traditionally through oil and gas, and we do the full scope of the early upfront G&G work to simulation work, and then supporting litigation, sustainability for all types of oil and gas plays. But we've also diversified our service offerings to capture more of the other up and coming industries or emerging technologies. And I'm specifically focused mostly on lithium and geothermal. But we definitely have a good working project base with carbon capture, utilization, and storage, and also we do a lot of sustainability work, and that can be through sustainable strategy, getting, providing technical advisory on regulations and policies, providing audit services. So that's another important component that is part of the GLJ base. Related to geothermal, we've done, a variety of projects across the globe, from Australia into North America and into Europe. And we support reporting resources, doing evaluations and helping with planning and modeling. On lithium, it's the same thing where we've supporting projects in Europe primarily, but we've also supported projects here locally with E3 Lithium, Lithium Bank, renewable geo resources, and indigo exploration, and hoping to see that really take off here in Alberta as a local commodity. And just kind of lastly, just to give you an idea of some of the projects that we're involved in, some of the bigger projects that you might be familiar with is Ever Technologies. Obviously, they're Alberta based, and we've been doing lender technical advisory for their project in Germany. We're also doing competent persons support for the Vulcan Energy project in Germany. So, two big projects in Germany, and then doing some smaller projects that have been focused in Australia, some in Africa, and then also Ukraine, Alberta. Yeah, so I just wanted to go through that real quick, give the plug for GLJ, and I'd like to give one more plug for World Geothermal Congress. As everybody probably is aware in here, that we will be hosting here in Calgary. There is opportunities to get involved through sponsorship, volunteer. I think there's a specific section for student volunteer opportunities, so definitely something you guys should check out. See if you can get involved in that. It'll be a big event. It's not happening for another year, but they're already getting rolling on lots of planning activities. So definitely a good thing to get involved with. And with that, let me switch over and I will hand over to the students, give them a quick introduction. Okay. All right. I'll welcome Daniel, Raj, Nandan, Anika, and Gavin up here. They're going to present their project that they presented at the Imperial Barrel Award earlier this year. And it's on the Newberry Volcano in Oregon. Why don't you guys come on up? Try this or at the Hubble. Okay. Yeah.
All right. Good afternoon. Thanks so much, everyone, for joining us. Welcome to our IBA presentation. So for those of you unfamiliar with the IBA, it stands for the Imperial Barrel Award. It's run by the AAPG, or Association of American Petroleum Geoscientists. So the competition is a global subsurface basin analysis competition for geoscience graduate students. So basically, we're given a data set and we have 8 weeks to analyze it. And we chose the discipline of geothermal, but there's also petroleum and carbon capture and storage. So ours, I guess without further ado, I'll introduce our geothermal exploration and development at Newberry Volcano, Oregon, USA. I'm Annika Richardson. I'm a first-year Master of Science student at the University of Calgary. I actually mostly study environmental seismology, so I was branching out a bit here. And I'll let my teammates introduce themselves.
Hi, I'm Gavin Woodburn. I'm a Quaker First Nation member and PhD student at the University of Calgary. My research is actually more focused on regenerative forestry and bringing together Indigenous science with the research. But I still really like geothermal. I think it's a really cool subject.
My name is Daniel Falabi, PhD student, University of Calgary. My present research focuses on geothermal exploration assessment in Yukon province, especially in areas around the Teslin Fault and the Delany Fault.
Hello everyone, I'm Nandan. I'm second year MSc student. My research is focused on heavy oil recovery. Am I audible? Yes. Hello, I'm Nandan and I'm a MSc student of petroleum engineering. My research is focused on heavy oil recovery. English is not my first language, so pardon me if I spell anything wrong.
Hello everyone. My name is Raj. I'm recent graduate from University of Calgary. I did Master of Engineering in Petroleum Engineering. My area of interest is reservoir engineering and particularly asset valuation and obviously the geothermal development and exploration. Thank you.
All right, so we'll get right into it. At Newberry, we are recommending drilling 1 to 2 wells in a 15-kilometer squared area around our key well 5529. The system we would like to implement is an enhanced geothermal system, and we'd be targeting temperatures between 175 degrees and 300 degrees Celsius. That upper limit is set by engineering needs, and we have a pretty high temperature gradient in that 15-kilometer squared area, well above crustal averages at 109 degrees Celsius per kilometer. That depth interval that we'd be targeting is fairly broad, from 1,600 meters to about 2,700 meters. And at depth, kind of on the deeper end of that depth interval, we would be looking at brittle felsic intrusive rocks as well as basalts. We've estimated a reservoir volume in that 15-kilometer squared area of about 10 kilometers cubed and about a thickness of 1,200 meters. This area is also really exciting because it's prospective for super hot rock geothermal, so new technologies, which, you know, we got to test out if we want to move forward. I'll hand it off now to Gavin to chat about sustainability.
So when we were approaching this project, it was crucial that we were meeting the UN Sustainability Development Goals, because we want to make sure that our project is keeping up with global needs to combat climate change and various other subjects within it. And a geothermal project could really touch on all of these, but we actually decided to focus on 3 goals in this one, being Goal 7, the affordable and clean energy, Goal 9, build resilient infrastructure, promote inclusive and sustainable industrialization, and foster innovation. And Goal 13, to combat climate action. But we also wanted to help approach Oregon sustainability goals. Since this project is happening in Oregon, we want to make sure that this project is also benefiting the state and what they want. So one of their goals is to have net zero emissions by 2050. And then from that, go on to 50% of retail electricity being sold from renewable sources by 2040. And then the other one was reducing pollution to enhance public welfare of at-risk communities. And one example of at-risk communities by this definition would be Indigenous communities in the area. So for this one, we're focusing on helping a nearby Indigenous reservation who is very remote and doesn't have access to energy or economic opportunities. So this project is actually a way to help bring together a financial opportunity for the people in this area and actually build good relationships.
All right, so getting into the geology. So on this map, you'll see a red star. That is Newberry Volcano, and it's located on the North American continental plate at the intersection of 3 tectonic provinces. So fairly complicated geology and kind of tectonic setting going on. We have the Blue Mountains to the north, the Cascade Arc to the west, and then the extensional basin and range to the south. Newberry Volcano is actually bimodal. So what that means is it erupts equal volumes of felsic and mafic lavas, which is really interesting. Generally, those felsic lavas are rhyolitic, and they have regular recurrence intervals, whereas the basalts do not. All right, so Newberry Volcano is still marked by that little red star in the middle, and it's important to understand regional stress patterns and structures in any geothermal or any play for that matter. So these include more local structures like the Northwest Trending Brothers Fault Zone, the north-south trending high cascades to the west, and again, that basin and range, so an extensional setting in the south. It's worth noting that the high cascades have a lot of other active volcanoes marked by those red triangles. So pretty prospective for future geothermal developments. And that mountain range even extends up into Canada, like Mount Meager, kind of near Pemberton. Other sites of note around Newberry Volcano, as Gavin mentioned, the caldera is actually a historic site, an archaeological site important to the Warm Springs Reservation. So no drilling there. And it's also a national volcanic monument, so important for local tourism and recreation. So the drilling site is just outside of that. Going into how we did the analysis. So how the IBA works is that they hand you a data set and they give you an area where your data is from the AAPG, but you cannot collect any other data from that area. So generally it's an incomplete data set. And what we did was we supplemented a little bit by looking at the literature, but mostly we were analyzing kind of the remaining things on this slide. So we had one key well, 5529. You'll hear us talk about that a lot. It had merged LAS files with a suite of gamma ray, SP, neutron density, neutron porosity, and resistivity data. On the well log on the slide, it's been simplified just because that would be really messy to show. So we used Petrel to analyze the well log data set and also to produce the geophysical model that we'll present shortly. The geophysical model was based on gravity and magnetotelluric surveys that we were given by the AAPG. And then our engineering analysis was a little bit trickier, just having that one key well, but we did supplement with some values from the literature, which you are allowed to do. So we'll get into the geology a little bit. So we had some basic lithology given to us. So what we did was we simplified it into 4 main lithoclasses. And this was based on facies distribution within each major unit, as well as the surfaces that were identified in the geophysical model. So trying to match the structure and the geology. On the simplified well log, you can see the facies legend. It's kind of that colorful basalt, dacite, tuff, etc. on the side. And this was used to determine the 4 lithoclasses. So there's the upper John Day and the lower John Day, which you'll actually find in the literature if you look at anything to do with Newberry Volcano. The 2 bottom units, so the transitional volcanics and the felsic intrusives, are purely named for the purposes of this project. And we are actually targeting drilling at about 2,500 meters. So that's at the deepest bit of the transitional volcanics and the top of the felsic intrusives. So I'll zoom in here on the next slide to a section at about 2,500 meters on the well log, just to give you an idea of what the geology, the simplified geology down there looks like. So we can actually see, is what's interesting is there's 2 areas that have been previously fracked. Those are marked by the dashed green lines. And those projects, they were EGS as well, they were actually unsuccessful. So that was important for our analysis to take a look at what happened with these projects, why did they fail? So we'll discuss that a little bit more in our engineering section. So to get into this, I'll be passing the mic to my teammate Daniel, and we'll take a step back, look at the geologic structures in the area using our geophysical model.
Thank you. All right. The image in the right panel is the LiDAR image pulled from Grasso et al. 2012, and it shows the demonstration of the regional stress field of the area. In the north, we have the northwest trending fault. In the south, we have the northeast trending fault. And in the center, we have the approximate north-south trending fault and the ray fault around the caldera, where we have 2 key wells. The red is the well where we have the most geological information, and the green dot is the well that has the highest recorded temperature. On the left panel is the 2D surface map generated from the inversion of the gravity and the magnetotelluric surveys. The whole study area was analyzed where we have information, but then we concentrated majorly in the center where we have that red line to have more information of the subsurface around the keywords. This is the density profile. The low density relates to loose or unconsolidated geologic materials. And this can be observed in regions around the caldera towards the east. And then on the second layer, we also have evidences of clear alteration from upwelly geothermal fluid. And this correlates also with previous studies in the area. And high density anomaly relates to consolidated geologic materials, and we see this to wrap around the caldera from the west to the east. And also, we observe a high density anomaly that relates to pluton intrusion in the west. And this is the heat source, where we have the key well penetrating, well 5529. And also for the resistivity profile, we have low resistivity that relates to unconsolidated material, which also relates to geologic formations that is filled with water, or probably saline solution or clear alterations. And this can be observed around the caldera and in the second layer, correlating well with our density profile. The trends from the density and gravity, from the density and resistivity, were used to constrain the extent of the pluton intrusion and the caldera. The white line, dotted line, indicate the extent of our caldera towards the east, where we have our the well with the highest recorded temperature, and the yellow line indicates the extent of the pluton intrusion, where we have our key well penetrating, well 5529. So several surfaces were picked, and these surfaces were picked from the inversion of our density profile and our resistivity profile. These surfaces were averaged to give 5 surfaces, and this corresponds to the boundaries of our geological boundaries interpreted from our log. And so these boundaries are the upper John Day Formation, the lower John Day, the transitional volcanics, and the intrusives. Also from this, we discontinuities in the anomalies from the resistivity and density were used to pick the faults in the area, and these faults were observed to also correlate with the regional stress field, where we have the approximate north south trending fault in the center part of the study area. And the extent of this fault is not known, and that's why we have it to be dashed towards we have solid lines and dashed lines. That's because the extent of the fault is not known. And but we know that the fault does not extend to transitional volcanics because it has a low natural permeability. And that's one of the reasons why the previous project failed in the area. And so also our key areas, our target formation is between the transitional volcanics and intrusives, majorly because the zone has high density and high resistivity, indicating that it is brittle and would not easily collapse when drilling, and which is good enough for a good geothermal project. But another fact is the high resistivity and high density indicates that the place our target formation has low heat convectivity, has low convective heat flow, which also could be responsible for the failed project in the area. So this is the 2D surface for the lower John Day Formation overlying our target formation. The red color indicates areas of pluton intrusion and our elevated surfaces, and yet it's widespread. But going towards the transitional volcanics, which is our target formation, the extent gets reduced. And so I will show images of the 3D surface generated from the joint inversion of the density and resistivity. This is the ground surface where we have, so there are 2 features here, the Paulina Lake in the north and the East Lake in the south. So the trends from the resistivity were used to generate this. And underlying it, we have the boundary of the upper John Day and the lower John Day formation, where elevated surfaces are the brown color, and these are seen to be widespread across the study area. Our target formation is a boundary of the lower John Day formation and the transitional volcanics, where this Pluton intrusion are observed to have varying direction. We have the northwest southeast trend. Some are trending in the northwest southeast direction, some in the approximate north-south direction. And the different orientations of the Pluton intrusions reflect the very stress field of the region. And we see this extent of the Pluton intrusion reducing as we get to the boundary of the transitional volcanics and felsic intrusives. A key point is that the widespread volcanism in the region establishes the fact that the place is a viable source of, is a viable site of geothermal potential because of the heat source, which is an important component of geothermal development for a geothermal setting of this nature in a volcanic region. So this is the bottom of the felsic intrusive formation, which was used to generate the thermal graded map of the study area, which will be more explained in details by Hanifa.
All right, so I forgot to mention we did have some bottom hole temperatures, which is pretty critical for geothermal exploration. So with those bottom hole temperatures, we had about 15. So single data points, which are marked by those white squares, and then the labeled wells on the target area figure. We did a very simplistic calculation to produce this temperature gradient map. So we calculated the variations in residual temperature gradient. So that was using the linear relationship between temperature gradient and depth. And the way this ties into the geophysical surfaces that Daniel was just talking about is we used the trend of that deepest surface to fit the map. So overly simplified, but good for our purposes, we can see that our target area, which is marked by the dashed red rectangle in both figures, is well within the higher geothermal gradient area where we can drill. Our key well, 5529, is marked by that red circle. So that's where we were pulling a lot of our data and our analysis from. We also need to acknowledge, as I've kind of mentioned, that the target area is limited by the National Volcanic Monument, which is marked in the target area figure by that dashed white line. Sorry, it's a little hard to see, as well as the caldera being a archaeological site. It's kind of interesting to see that the caldera has some really anomalously hot, shallow wells. So that's marked by that green circle. We'll get into it a little bit more. We have some temperature profiles in our engineering section, but just kind of something of note, maybe some uncertainty there. And finally, on the geophysics and geology side of things, we made a very basic geological model. So what we did was we wanted to conceptualize the geology because that's important, as well as the temperature gradient in our target area. So again, this is an oversimplification, mainly because we just had the one well, but we took our gamma ray lithology indicator and extrapolated it at low resolution using our geophysical surfaces. So you can see the temperature isotherm of 200 degrees. It's fairly schematic, but gives you an idea of where we'd start hitting those target temperatures at that kind of minimum. So, this is a good visual of we didn't have a lot of data, and something that we could do that will kind of increase our chance of success is just do some data gathering. We know there's deep wells that have been drilled in this area. So, simply going in and getting that data will give us a lot better understanding of what's going on at depth, what's the continuity of the formations, and give us a lot more certainty for this pilot project. So with that, I will hand it off to Nandan and Raj, and they will discuss our engineering analysis.
So far, we have discussed geological and geophysical model. And in this image, it's a colorful LiDAR image. We are seeing all the available wells in the location. The red dot and green dot are marked as a reference that those are used before as well. Red dot is one of the deepest well available in the location, and our key well 5529. And the green dot is one of the well within the caldera. It was drilled before the monument declared, and there are three more deep wells within the location. All the wells are located in northwest region of the caldera. You can see also a monument bounded by green line. Uh, uh, and all other wells are just shallow wells. Their purpose is to measure temperature. To make an engineering model, we have to get we need to follow some checkpoints. So first is extent of our target reservoir rock. We have those extension of a reservoir rock by a geologist. The reservoir area is roughly around 10 to 15 kilometers squares. We also know the structure of reservoir by density and resistivity data. For the depth, we are using temperature gradient. The left figure shows temperature gradient of deep wells, those four deep wells. We have expected range of temperature around 170 to 300 degrees Celsius, which gives us quite a good range of 1600 to 2800 meter depth. Right figure shows temperature of shallow wells, and there are two odd figures marked with red arrows. They are reaching very high temperature within short range. That is because it is is over the hot caldera, hot magma chamber, and all the other data like thermoconductivity and petaphysical data like permeability and porosity is taken from the log and literature. Now we are getting into more details of 5529 well. It reaches up to the depth of 10,000 feet and temperature of 330 degrees Celsius. We are seeing in this figure, we are seeing casing profile of that 5529 well. We can see that liner installed in the open hole section. It's roughly around 6,000 feet. On the leftmost figure is a lithological scale made using mud logging. On the open hole section, we are almost encountering every possible igneous known to me, stuffs, basalt, granodiorite, andesite, and combination of more types. For thermal conductivity data, we are using actual core samples and cuttings. So they did direct measurements on those core samples and corrected for situation using famous Blackwell's paper. In the open hole section, conductivity is fairly normal, and it has average value of 2.14, which is a good thermal conductivity for a rock. We also have one pretty detailed log of BHTV of open hole. From the location of all the fractures in that BHTV log, the SHM direction is roughly east-west direction. And to know the aperture and fracture counts, we plot it. So we are seeing this bar graph for fracture count, and the green line is for fracture aperture. The graph is just plot for open hole section. We can see fracture is pretty much consistent throughout the open hole section. If we ignore the initial spike of fracture aperture is also pretty much normal and consistent throughout the open hole. From the stress analysis, SH max and SH mean has reasonable difference. So, and that is also good for fracture stability. Now we will talk more about failure analysis.
So far, we have seen what are the data we need from the geologist and geophysicist. For an example, formation and the fracture tendency of the formation, But before we move into the development scenarios, it is very important for us to look at what went wrong in the previous project. We forget to mention earlier that the development and the exploration activity in this area was started in 2008. Several attempts were made to create a fracture and effective EGS reservoir. The last was during the in the 2014, and I'll walk through like what went wrong based on our analysis of the detailed report published by the operating company. Um, they plan to create EGS reservoir in three different sections. So if you look at the image on the right hand side here, there are three sections and they started from the bottom. So what they do, they create a fracture just like similar to the our oil well fracking techniques. They create an bottommost fractured reservoir and then they isolate using a material, gel-like material. It's called effective diverter, so they can move ahead and create fracture in the further section. So we observed that the diverter performance was not so promising. The diverter was not so effective. So when they moved ahead to create another section to frac, the the fracture fluid was leaking into the fractures created in the above zone. The second cause was insufficient pressure. So all we know, we are injecting a pressurized fluid to create fracture in our reservoir. So we need to exceed a certain minimum, which is called minimum horizontal stress. So in the previous project, the pressure was very limited because of the wellhead issue. They encountered the fluid was leaking from the wellhead, so they couldn't go beyond a certain limitation in terms of the fracture pressure. The stimulation duration to create fracture was not so long enough. We know like the formation was igneous and it has higher strength compared to our sedimentary rocks. So the stimulation duration and the pressure to create fracture in igneous rock will be way more higher than conventional sedimentary rocks. And as a result, they couldn't crack the reservoir enough to create effective and commercial EGS reservoir. Other factors um, that affected the operations were high temperature, as mentioned one of my team member that the temperature exceed up to the 300 degrees Celsius. So at such high temperature, there might be some equipment that might not function effectively. And obviously, there were complex stress region. The stress profile were very dynamics because of fluctuation in the temperature. So they were injecting fluids, so cooling and heating, depending upon the heat supply from the heat source. So moving ahead to the simulation aspect, this is our ongoing work to simulate different case for the geothermal development scenario. Our base case was to model the existing condition with the same fracture density and the fracture permeability that the operating company created back in 2014. And our second case was to single well coaxial model, and the case two is closed loop YouTube model, which is very similar to the term we are familiar with the ever closed loop model. And our third case is EGS reservoir with multi-stage fracture model. As we know, we have a very like large bottom hole section which can be fracked more than, and the length of the open hole section is like around 1 kilometer. So we can frack different stage. We can frack the different portion of the reservoir. I'll hand over to discuss the Monte Carlo simulation that we performed for development scenario, and it will be discussed by Nandan.
Thank you. To know the heating place of our region, we perform Monte Carlo simulation. We use a simple equation of heat transfer to know how much heat we have subsurface. and convert that heat into power. We use some conversion factors and industry standards. We have area of pretty much 10 kilometers square, and all the thickness, densities, and all other properties is discussed before. I want to note that temperature of reservoir is roughly around 270 to 300 degrees Celsius, and our base temperature is 180 degrees Celsius. We are using recovery factor of just 20%, and conversion factor of that heat into the power is roughly around 10%. I assume load factor of that power plant is 95%, which is the maximum operation efficiency of that plant. We run 1001 run of Monte Carlo simulation, which is an industry standard, and plot this roughly normal distribution curve. It has P P90, P50, and P10 line, which is 90%, 50%, and 10% statistical probability. If we plot that Monte Carlo simulation of normal distribution into cumulative probability, we can see that we have, even if we consider a P90 case, which is the lowest amount of electricity generation, which is around 70 megawatt, we can power roughly 49,000 homes. The conversion of 1 megawatt is equal to 700 homes is taken from one of the internet source. One noteworthy thing is Bend, Oregon, which the nearest town near this location has only 41,000 homes. So even if we consider our P90 case, we are exceeding the household of nearby town.
So after we compiled all of this data, we want to take a chance to actually look at what might the risk be going into this project. We've done sort of our preliminary analysis, looked at the literature. And so what we actually did was we took a petrology risk analysis, the Pete Rose method, and we just kind of adapted it a little bit to match our geothermal needs. And so we just took a moment to think about what are our biggest risk factors within this project. And one of those ones we looked at was the reservoir. We know that there was past issues with this in other projects, but we feel like we had enough knowledge going forward that we can kind of address and move past these things. We then looked at the economic viability of the whole project, and this was definitely our best category because we know there's great benefit to this project being introduced into the area. And so we have no concerns really about the economic viability of the project. Then by looking at the engineering, thinking about the drilling, the reservoir stimulation, given a lot of those issues in the past projects, this was probably our more riskier area. It also just comes with less data overall for us to look at. But overall, we feel pretty positive about addressing this issue moving forward. Then thinking about the geological, this was another area where we know there's definitely some challenges given the igneous and the complexity of the geologic profile. But we have quite a lot of literature around the area since it is a national monument. We have archaeological information from the area. So there is quite a lot of data about the geology. So we feel pretty good about that moving forward. And then environmentally, this is also another riskier area just because we are in close proximity to national parks. We're in proximity to a lot of volcanic hazards where not only the volcano hasn't erupted in a long time, but there is a potential of other volcanic hazards. And of course, just sustainability of bringing a project like this to this area. So overall, we start off the project based on the Pete Rose method of getting a 16% chance of success. And based on how this risk analysis goes, and given how it's a industry standard, then that's why we chose it. 16% is actually quite good for when we were approaching this. So we believe that 16% chance is actually beneficial for doing the next steps, because this is just based on the first little bit of data that we got, our first little bit of analysis. And we think that, yeah, this area is definitely a good area to move forward with. So thinking about the state of Oregon, we wanted to think about how this project would fit in to their energy needs. So you can see in the biggest blue circle, most of their energy is produced by hydro sources. And then looking at the red and the gray circles, you see that together is about the same coal and natural gas as hydro. So there is still a lot of not clean energy being produced within the state. And some key points to mention here is that while hydro is big right now, last year, the state of Oregon and Seattle, who are two major hydro producers, actually recorded half the amount of hydro that they usually produce. And this is mostly due to climate change. There's just less water running through in the summers, but also aging infrastructure, because a lot of this infrastructure was built a long time ago, and it's going to be costly to build that up. And so what ends up happening is they have to supplement their coal and natural gas, which typically comes from pipelines from Canada. So they're then purchasing more gas from us. But thinking about the potential of this project and thinking about the Monte Carlo simulation that was done, based on the total geothermal that's happening right now in Oregon, this would increase their geothermal production by 500%. So quite a lot, and have the potential to generate electricity, 112 megawatts, being able to completely power the city of Bend nearby, as well as the Warm Springs Reservation, which is not too far away. And thinking about how much their electricity bills are right now, and thinking about what the U.S. Powered Energy Department says, we could actually lower electricity bills for these places by 65%, bringing their average electricity cost from $2,150 to $750 annually. And based on the amount of greenhouse gases that are produced from a single home, we could reduce up to 447,000 tons of carbon dioxide. So based on this data, based on our preliminary results, our first recommendation is actually to partner with the Warm Springs Reservation. This isn't just fulfilling a moral duty, but it's also, in the case of Canada, it would be fulfilling the right and duty to consult with First Nations. But to start a project before it's actually planned, you actually know what you want to do, to start a project at the very ground level with the community means you're not just fulfilling a moral duty, you're fulfilling you're fulfilling a right and the ability to add a partner to your project. This isn't just a checkoff that you can do. This is actually an opportunity for you to bring in a partner that not only can help you financially, but also environmentally. And there's a lot of examples in New Zealand, for example, where Maori communities are partnering with geothermal projects, and the results are actually quite similar based on many of the geothermal projects going on. And the projects are finishing early. They're finishing with less workplace injuries, and they're fulfilling more of a balance between the geothermal and the extraction that's going on with the environment by incorporating Indigenous science and Indigenous values around the project.
To summarize the main technical takeaways from this project, obviously we cannot create a full field development plan based on the data from only a single well. We need to know the field more in efficient way. That's where come our third recommendation, to drill 1 or 2 wells surrounding the target well, which is 5529. So we can get the more data about the volcanic field, and we can also develop a new geothermal or latest modern geothermal development strategy, which is Ever's closed loop strategy. And instead of fracking the reservoir with the hydro shearing technique, we can implement the hydraulic fracture technique, so we can have enhanced permeability in our EGS system. And testing a new technologies like super hot rock geothermal, which is like more efficient drilling techniques, can be beneficial to this project. With this, I would like to conclude our presentation here. Thank you so much for listening to us, and special thanks to our mentor in this project, Harsh Gilbert and David Embry. Thank you so much.
So we'll let you guys ask any questions if you want. We have a few minutes for if anybody has any questions.
What indigenous science are you incorporating into your analysis and into your project? So I'll just repeat it here. What indigenous science are you incorporating into your project?
So for what we've done so far, we actually can't really say what indigenous science is going to be incorporated because this is very much a place-based area. And indigenous science, because it's so place-based, and I'm not from this area, it's not really for me to say, but by creating that relationship from the ground level, you can let the community guide what that knowledge is going to be. And generally, it's about their history and their knowledge of the land from being there for thousands of years, generations. And given the archaeological significance of the territory of the volcano to them, they may have unique knowledge that is not, you're not going to find in literature. So that comes with building the relationship in a meaningful way.
Right. Any other questions here? I don't know that I have the ability to gather questions from online, unfortunately, but oh, of course you do.
What's that supposed to mean? Thanks for the presentation, everyone. There was a lot of good work. Unfortunately, there is an incredible amount of data associated with Newberry. Have any of you looked at it since completing this and doing the presentation? And if so, how would you modify any decisions you've made based on that?
I can start. I mean, based on the way the IBA competition is structured, you are fairly limited with time in the analysis that you can do. But absolutely, there's a lot of data, and also just a lot of data we didn't have access to even kind of put into the presentation. So one thing that comes to mind is we didn't even touch on induced seismicity. Like there is some papers on that in the area, so that's a risk kind of that we haven't considered. Other things include there's a lot of really simple models that we've done in this project, more based on time constraints, as well as experience. A lot of this was new to us, the different types of analysis. So it was a great opportunity just to learn more. But we basically had a layer cake model for our engineering simulations, and obviously that wouldn't fly in real life. So I think just really digging in and properly making the models and properly making the maps, and not kind of taking the shortcuts we needed to do to get this done in the time frame that we had. I mean, I don't know if I'm really answering your question, but that would kind of be a start for me, if that makes sense.
Yeah, and I can add a little bit too. I mean, just given the new political state since we started this project, when we started it off, they encouraged us to look at some of the socio impacts of this project and recommended us to this one sort of guide to assess that. And obviously, when the new presidency came in, that was now gone. And so there's also been a lot of changes to resource extractions within national parks and other areas. So based on some of the new political changes going on, that would, from the ground level, allow us to access different approaches to the project, really. And one of the big ones has fairly new information around is sort of regarding the water and the current project that's going on at Newberry. And they're doing a closed loop. Or is it super hot? Okay, but they're essentially there is groundwater north of the volcano, but they're extracting it from the town of Bend. Based on that, they would only need to extract it one time and then be able to reuse it. And basically, their analysis was that it would be the equivalent of one hot summer day's worth of water from the town. So not a huge impact that way, but to get groundwater, be a bit tougher.
I got a big list if nobody else has questions.
We'll give other people a chance if anybody wants to ask a question. Otherwise, I'll give it back to Dennis, of course. I'll ask a quick question. On the resource estimation, how did you find that process and coming up with a recovery factor?
For the we have seen so it's my first time of doing that Monte Carlo simulation. So I was referring a few papers of resource assessment, and there is some general value of recovery factor 20%. So I just assume that the recovery would be more or less 20% optimistically.
Okay, yeah. Well, a lot of people end up doing that, but yeah, there's a lot of considerations that need to be part of that, but it's definitely not an easy process. Dennis, did you want one more question? We got
1, 2.
Okay.
With the electricity, you guys were estimating 10% conversion, but even with like the newer organic Rankine cycles, you were getting 12 to 15%. And we look at the flash, they're well over 20. So what would it look like if you actually use those better numbers?
We can use that better numbers, but again, I'm not familiar with this kind of Monte Carlo simulation of resource assessment. So I was just using the least number available in the literature. So it's 10% to 15%. So I just take 12% and average.
So there's upside then.
With your Monte Carlo simulation, did you consider any sensitivity analysis to your input parameters or like ice plots or tornado plots?
I want to use that that sensitivity analysis, but I haven't done that in time. So it's just primitive model. I use normal distribution for all the parameters available. Whenever I have this kind of percentage of recovery factor or conversion, I use triangle method, just a normal distribution.
Okay. Back on slide 31. So you guys had talked about re-stimulating and fracturing, which you had talked about that's what caused failure. But on your like, do you have flow rates in here that you were able to use to predict what your total potential generation capacity would be? Or
Yes.
was that because all that's based on the assumption that your fracking and your hydrostimulation and everything else would be effective?
Yes, we did those kind of simulation using CMG. I guess I'm not the better person to answer that question.
Yeah, in terms of the flow rate out from the well, we just put the well constraint as around like 50 meter cube per day, and we ran the stimulation like purely based on the whatever the well constraint that we have as per the industry standard.
All right. Well, we're about 1 minute. Let's thank the students for their great presentation. Yep. And I'd just like to thank some GLJ support, Haley and Bianca, who helped to get this set up, and Nathan. Thanks to Geothermal Canada for helping to host the webinar. I'm not sure if we actually got all of our attendees into the webinar, but I think they're recording it. So watch for a posting of releasing that on the web, which would be great. And yeah, thank you everybody for attending in person and online. Have a good day.
I'd like to give a minute.